So I'm recording. Okay. Before we start, okay. So I need to move things around a little bit. Like I said, I discovered that we're losing a whole day because the last day of class turned out to be a Tuesday instead of Wednesday. So I'm losing 2 lectures that way. Because of that, I need to have another makeup. I'm sorry, but we're losing a whole day of lecture by having the last day of class on Tuesday. Next time I offer this class, I'm gonna move it from Wednesday to Tuesday, so I don't lose a class. So, we will have another makeup like next Monday, the same as today. You're not gonna be here?
Yeah, I will.
Yeah. I'm sorry, but either I teach the material or you will have less education. So this is for your own good, okay? I know you as students, me as a student, I won't like additional lectures, but thinking as your mother. So, bear with me, I really have your best interest at heart. So I really want to get the information to you. So if you have other plans, if you cannot make it, lecture will be recorded. Your in-person presence is appreciated for your own good again. But we have to have that. And then, Priyanshi and Brittany, I'm moving your presentation to the 26th of April. Okay, so moving it 2 weeks. So now we have a midterm or exam 2 on April 19th. Here is my suggestion. Who wants to have a take-home exam? Instead of then I can use the time for lecture, and then you can take it home and you will have a weekend to answer. So who wants a take-home exam versus in class? With open book, open everything. So it would be open, the weekend of instead of having it on the 19th, then I will open it for you, let's say on the 19th, and you turn it in by Sunday midnight. Okay.
Wow.
Will you make it even more difficult because
Yeah.
it's open book? No, I would.
No. That won't be more difficult. It would be that obviously it won't be something that you have to memorize.
Okay.
So it would be something to think. So that's why you will use your note. I've done it before. It's not like experimenting with you guys. We've done it before, take home exam. And students as well, so.
I'm not gonna lie, that takes the edge off of the extra lecture. That makes it better.
Okay, so it's compromise?
Yeah.
Thank you, guys. I appreciate the flexibility. I just wanna, educate you as much as I can. I was so bummed learning that Tuesday was the last day of class. So we were just like, what are I doing?
I
Yeah.
have a question, because their presentation got moved to April 6th, isn't that when Jean and I present?
Yeah, so you
Okay.
will have to presentation.
Okay. Oh.
Now, with the take-home exam, we won't have a presentation on the 19th. Unless you wanna go on the 19th. Instead of the
Thank
26th.
you.
What do you want? 26, yeah. Then we will have on the 19th, we'll have full lecture. On the 26th, it might just be presentation. If we have the extra, then we might not have even a lecture on it. So, yeah, go ahead.
So instead of what? So if we have no exam, the lecture's that day, we still need that lecture.
Yes,
Because you're.
yes, because usually the exam day, I lose at least a lecture and a half.
Oh,
Yeah, so no, the lecture next Monday is going to happen. And then using the exam time for the lecture, that will be good for me to cover the material. Okay, are we good?
Yeah.
Are we all happy?
Yes.
That sounds good, yeah.
Okay, good. You'll be fine. You're gonna ace the class, don't worry. And you'll get so much information, you'll be the youngest protein chemist by the end of this. Okay, perfect. So let's continue. Where we left off, or we just started with enzymes, we didn't go very far. Are they proteins?
All the foods, the foods, yes.
Food enzymes are proteins, but we have ribozymes. These are non-food enzymes, and they're not proteins. Very good. Great. Enzyme definition. What's the enzyme definition? And how does it function? What does the enzyme do, Priyan?
Catalyst that lowers activation energy.
Yeah. Very good. It's a biological catalyst. It lowers the activation energy of a reaction. So do you remember the 6 different classes of enzymes? Or what do you know most? Hydrolysis? What?
Kinase.
Kinase. Was it? No, oxidoreductase. Ligase. There's one more, transferase, isomerase, right? So everything you know, easy, hydrolysis, break covalent bond and release H2O, okay? Or H2O is released, yeah, when you break the covalent linkage. Okay, transferase is one functional group, goes from one substrate to the other. Let's see, isomerase, like changing glucose to fructose in high fructose corn syrup. Let's see, liases, I'll give you an example of liase. It's the formation, removal of a functional of a group and forming a double bond. Like the hydrogen is for example. What was the last one? Ligase, forming of a covalent bond. Okay,
Wait,
formation of a covalent bond
ligase,
Ligase.
isomerase, transferase, hydrolase, that's fine.
and oxidoreductase, like peroxidase. Catalase. Yeah. Good, perfect. We'll keep that for next time. So enzymes are specific. What does that mean? You all know that there is a binding site and there is the active site. So you have the substrate is binding to the active site of the enzyme. So it has to be stereospecific. That means it has to be very structurally fitting. And that's why the first, is the binding covalent or non-covalent? Non-covalent, obviously, it's non-covalent interactions. All of the different interactions that we know of can occur between the substrate and the enzyme. It could be hydrogen bonding, it could be ionic, it could be hydrophobic, it could be van der Waals. So non-covalent interactions, okay. So there in 1894, very long time ago, over 100 years ago, there is the lock and key theory that there is a stereospecific complex, which is very true. It has to be very specific in how it fits with the enzyme binding site, the substrate. And then it used to be thought that the active site is rigid. That means the shape does not change of the active site. But that is not entirely correct. So this is the key and lock theory. We all think about it. And we always thought it was rigid until a few years later in 1959, talked about the induced fit theory. So the actual binding site is not rigid. It's impacted by environmental conditions. So the pH changes the ionization. That's why you have optimum pH, because then you have the optimum configuration for the substrate to bind. The ionic strength impact, sometimes enzymes require certain ionic strengths in order for it to perform or to bind to the substrate, and of course, the water in the system. So really, and not only the environmental factor, when the substrate binds, the site or the active site changes to fit the substrate. So it's really still a very specific, stereo-specific complex, but the active site is not rigid. It's not exactly like lock and key. It is very flexible site based on the conditions, environmental conditions, and then it takes the right shape for the substrate to actually bind, to perform the reaction and get the product. So this is the most accepted theory rather than the lock and key rigid site theory. Okay, so two events happen when we have an enzymatic reaction. So we're going to talk about enzyme kinetics. So we really need to understand what are these reactions that happen. First thing, enzyme is going to bind to the substrate and then get you an enzyme substrate complex. This reaction, E plus S into ES, it has a rate constant of K1. That's the first reaction that happens. Then, once you have the complex, then there is another reaction with another rate constant that gives you the product and releases the enzyme to make it again available for the substrate. So you have the forward reactions where you have the binding of the enzyme and the substrate, and then the formation of the product. Now, the ES complex can go backwards, okay? Can also the ES depletion of ES can either go this way, backwards, to release the substrate and enzyme, and can go forward. Now, when we are saturating the substrate, the enzyme and substrate, the reaction is more forward than back. Okay, so we have three rate constants, K1, K2, and K minus 1. That is the unassociation of the enzyme and the substrate. You all know this, so we reduce with the enzyme, we reduce the activation energy quite a bit to speed up the reaction like any catalyst. So that is just an illustration of how the enzyme works. So rate of the reaction, we're going to talk about kinetics a lot, and you're going to hear me talk about velocity. You have initial velocity and you have maximum velocity. So V naught or V0 for initial velocity and Vm for maximum velocity. So this is the rate of the reaction. So it is directly proportional to enzyme concentration. The more enzyme you have in the system, the higher your rate of the reaction. That's very straightforward. It's also impacted by the concentration of the substrate. Yes, the more substrate you have, you can get to Vmax. When you saturate, you reach to Vmax. Inhibitor, if you have inhibitor in the system, that reduces, in most cases, reduces the rate of the reaction. And then presence sometimes of a cofactor is important to enhance the rate of the reaction, enzyme cofactor. So we're going to talk about substrates, inhibitors, cofactors. And then there's the environmental impact. So we always hear about optimum pH, temperature, and ionic strength. So in general, if we are away 1 pH unit from the optimal, we lose about half the velocity or the rate of the reaction. If we go 10 degrees lower in temperature than the optimum, we lose more, up to 2 times the decrease in velocity. Okay. So it's very important that we understand enzyme kinetics, because we want to control the rate of the reaction, enzyme reaction. Why is this important? For us as food scientists, why is understanding enzyme kinetics and controlling the rate of enzymes important to us? Can you give an example where we really need to understand kinetics?
When we do enzymatic reactions. like
When we
this,
do enzymatic reaction, can you give me an example?
Hydrolyzing like whey protein.
Hydrolyzing whey protein to reach protein isolate, that's within
No,
example.
like the natural enzymatic reaction in food products like polyphenol oxidase.
Yes, so I want to understand the activity of polyphenol oxidase so that I can potentially inhibit it. And I have few examples of polyphenol oxidase. And if I know the Km, how the Km changes when I add an inhibitor, then I would know how much I need of an inhibitor to reduce the reaction of polyphenol oxidase. But other examples, like when we're producing cheese, I need to understand the kinetic of the enzyme I'm using, the rennet, whether it's microbial source or animal source, they will have different kinetics. If I understand, I know how much substrate I need, how much enzyme I need, it will determine the rate of my process, how efficient my process is going to be, and then I can regulate my production that way. So also, let's say if I'm producing maltodextrin, like sugar syrups or whatever, what have you. I also want to understand how much substrate I want, how much enzyme I want, and how much product I can produce in units time. So if I understand the Vmax and Km and I'm able to calculate them for every enzyme substrate combination or enzyme inhibitor combination, then I can control enzyme processes. I can control the quality of my products by inhibiting enzymes that are problematic, like polyphenol oxidase. So that's why we spend some time understand enzyme kinetics. Also, when I'm doing an enzyme reaction, like to determine substrate concentration, like glucose concentration enzyme, or when I am determining enzyme activity, or when I want to set up an enzymatic reaction and I want to understand how long I should keep my reaction. So all of this, as I design, like he said at the beginning, design enzymatic reaction, it's very important to understand enzyme kinetics so that I can devise enzymatic reaction for different applications. With that said, we're going to move into talking about the kinetics and how we calculate Km and Vmax. You've seen this before in different classes. I will spend a little bit more time. We tend to forget these things. They don't come naturally to us. So we're going to spend some time talking about that. And there might be a question in an exam that have to explain to me the derivation of the kinetic terms. So you're gonna love that. Chris is laughing. He goes, thanks, I'm not really taking this class.
No, it just seemed very obvious that was the case for you.
Okay, so when we have a reaction, usually we monitor the production of a product over time. So if I plot the time, the action time, and on my x-axis, and I plot the product concentration on the y-axis, I get a curve similar to this. So what is this curve showing? So there's few milliseconds at the beginning, we call it pre-steady state. That's when the P plus S, the time that it takes for the enzyme and substrate to form an enzyme to a substrate complex. And then the time lapses and then we get to a steady state. In the steady state, that's when the appearance of PS equals the disappearance of PS. That means the rate of the reaction of appearance, that means with considering the rate constant K1 equal to the rate of disappearance, which is a combination of going back and going forward. At this place where we have rate of appearance equal rate of disappearance, we call it steady state, and you can see it's linear. That's where we do all our measurements. We always want to be in the linear place of that curve. So the slope of this reaction is your initial velocity. Okay, so the slope here of this line, basically, is the rate of the reaction. The steeper the slope, the higher the rate of the reaction. Okay, so the steeper the line, the higher the rate. So what happens here? We see that we don't want to do any measurements of kinetics where we lose linearity and then it curves and then we reach a plateau. So what's happening up here? Why are we reaching a plateau?
There is no substrate.
That we are depleting the substrate, yes. So when we're depleting the substrate, we're not getting as much products up. So we lose the rate of disappearance being equal to the rate of the appearance. So here the substrate becomes limiting. So I want to make sure when I do any of my kinetics, I'm in this linear stage of my reaction, yes.
Can you explain the rate of disappearance equal to rate of appearance again?
Yes, so the rate of disappearance of ES, so when ES is formed, what's happening? The reaction continues to get new product and enzyme. So that's one way that ES disappears. Another way of ES disappearing is going backwards. Instead of forming a product, it can't be, E plus S can dissociate. So this rate and this rate equals the rate of deformation. When we are at a constant equilibrium of formation and disappearance, that we call the steady state, and that's where we get the initial velocity. We have the linear section of that curve. Yeah.
You said we only want to measure kinetics on like that one.
When
portion.
we are in the linear, because here that's not a good representation of the rate of the reaction, because now your substrate is depleted. So you don't want to be up here. The rate of the reaction is represented when the substrate is not causing a limitation. Okay. So in order to get the kinetics parameters, so I need to calculate Km, I need to calculate the max. These are important so that I can set up the reaction parameters. In order to get that, I need to create a plot that relates velocity to substrate concentration. Okay, so how do I get this plot? I would, at one substrate concentration and one enzyme concentration, I set up my reaction, and that's the product, and that is the time. So this is substrate concentration 1. I get the slope, that's V0. Then I do the same reaction with another substrate concentration 2. Then I get another V0. And I do it for multiple, at least 5 different concentrations. If I do that, then I can plot the concentration on the x-axis and the velocity on the y-axis. Then I would get this graph. So what do I see here? I see the parameters, kinetic parameters that I want to calculate. I see Km and I see Vmax. So what is Km again? Remember? Okay,
Substrate concentration at half, like Vmax by 2.
yeah, exactly. So Km you see it's on the x-axis where we have the substrate concentration. So Km is the substrate concentration at which I have half of Vmax. Okay, so that's my Km. My Vmax then, when I saturate the enzyme and I reach Vmax, above that, I don't increase anymore because you reach saturation and you reach what we call zero order with respect to substrate concentration. So now the reaction here, the rate of the reaction is no longer dependent on the substrate concentration. We reach Vmax. So I have Vmax, I have Km, I have substrate concentration, I have velocity, initial velocity. So I need an equation that relates everything together so that I can calculate Vmax and Km. So usually in order to calculate Vmax and Km, I have to be in the steady state of the reaction. I have to run my enzyme reaction multiple times at different substrate concentration. And then I would plot the relationship between the velocity and the substrate. Okay, this is not linear relationship. So Makila-Smenton equation is not linear, and we usually, as you know, when you do calculation, we like the linear relationship. If we take the inverse, it will give you a linear line and inverse of the equation. So I'm ahead of myself, but what we want to do ultimately is figure out an equation that we can use to calculate Vmax and Km, and we want to make that equation linear. Okay, so I want to find the relationship between initial velocity, Vmax, Km, and substrate concentration. That is my goal in order to be able to calculate Vmax and Km for every enzyme substrate combination. All right. So we explained initial velocity, we explained Vmax, and we explained Km as being the substrate concentration at Vmax. Why Km is important? Because it gives me an idea of the affinity of the enzyme to the substrate. So the next slide talks about what that means. So this graph here, you want to think about the red line as substrate 1 and the blue line as substrate 2. So the enzyme, I'm reacting it with substrate 1, and I reacted the enzyme with substrate 2. By looking at this figure, which substrate the enzyme has more affinity to? Think about it. Go ahead, Colin. Yes. Why? Because at lower concentration, I'm reaching Vmax half. So this means the enzyme has more affinity here. With the lower Km, I reach Vmax half or half Vmax at a less concentration than when I use substrate 2. At substrate 2, I need higher concentration to reach Vmax over 2. That means the enzyme has higher affinity to the substrate. So then it's an inverse relationship. So when I see lower Km, that means the enzyme has better affinity than having a higher Km. Okay? So both Vmax and Km are impacted by the nature of the enzyme, the substrate, pH, temperature, inhibitors. The only difference here that Km is not impacted by enzyme concentration. So it is definitely impacted by the nature of enzyme and substrate that will impact the affinity, but not the concentration of the enzyme. The concentration of the enzyme impact the maximum velocity. So the higher the concentration of the enzyme, the higher is the maximum velocity. However, if I increase the enzyme, it's not going to impact the affinity of my enzyme to the substrate. If I have more enzyme in the reaction, that does not mean that this enzyme is going to have better affinity to the substrate. Yeah. So everything else in terms of what they're impacted for is similar. Impacted by. So in processing or in food science, sometimes low Km is desirable. It has good consequence. That is when we are using the enzyme for production purposes. And here's an example: we're producing corn syrup with 40 dextrose equivalent. So with a low Km, I can have a high rate at lower concentration, more product in a shorter period of time. So this is great. But in other cases, low Km is not desirable. So here is choosing the enzyme that gives me the better affinity, the lower Km is what is desirable. But other enzymes are not desirable, so we don't want this to happen, like in oxidation browning, you don't want that to happen. Lipase activity for storage stability of fat, we don't want that to happen. So we don't want to have low Km for undesirable reactions. That means if you have low Km, this means we need to add more inhibitors to inhibit the reaction. That's more costly. Okay, so depending on where we are in our process, sometimes it's desirable to have low Km, sometimes it's not. Okay, and this is a reminder of first order, zero order. So when I am measuring substrates, I really want to be in this linear range down here. So I want to work with substrate concentration lower than Km. To really be in the linear range, so any small change in substrate is going to give me a significant change in the rate of the reaction. So that's why if I'm measuring constituents like glucose, I really want to work with very low concentration of the substrate so that I can detect small changes in the rate of the reaction. And that is why I want it to be first order with respect to substrate, and the enzyme is not limited. So when I'm designing an experiment to measure substrate or constituents, I want to work with concentration much lower than the Km, where it's first order with respect to the substrate. When I want to measure enzyme activity, I don't want the substrate to be limiting. I want the enzyme to be really up here, saturated with the substrate. Then any change in enzyme concentration is going to impact the rate of the reaction, where the substrate is not limiting. Therefore, it would be zero order with respect to the substrate. It's not impacted, its concentration is high, but the enzyme concentration is the first order reaction. Then I can use that setup to measure enzyme activity. And in analysis, we either measuring enzyme activity or we're measuring substrate or constituent concentration. So that's why understanding Km, knowing where the Km is for the substrate or enzyme, will allow me to choose my substrate concentration. So again, I'm cementing here in your thoughts why it's important to study enzyme kinetics. Okay, now I want your full attention. How tired are you today? Brain-wise? Very tired? No, come on, it's Monday, you rested 3 days. Whoever came on Friday, it's not my responsibility. I told you not to come. Yeah, okay, so I want to, like I said, I want to calculate my VM and KM. And I can control the substrate concentration, I can control enzyme concentration, I can calculate initial velocity by getting the slope, by looking at my time and measuring product over time. So I can get the velocity, initial velocity, I'm in control of the substrate concentration, then now I need to use this information to be able to calculate Km and Vmax. Right, how am I gonna do that? I need to figure out an equation that allows me to calculate Vmax and T. All right, so we're gonna look at what given we have. All right, so initial velocity, V0, what is it equal to? Initial velocity of the reaction, so we're measuring product, right? So it is the rate constant of the reaction going from ES to E plus. So rate constant of that reaction multiplied by the concentration of the ES complex. So that is the initial velocity. That's how we calculate initial velocity. Okay, now we know that. We also know that the rate of disappearance of ES. What is the rate of disappearance? So I have two reactions for the rate of disappearance. I have ES going to E plus S, and I have ES going to E plus P. So I have two rate constants. I have this rate constant going backwards, and I have this rate constant going forward. So this plus this is the rate of disappearance. Okay, I have the rate of appearance as the next given. The rate of appearance is ES. So the first rate constant, K1, multiplied by the concentration of the substrate and the concentration of the enzyme. What did we say at steady state? What do we have at steady state? Rate of disappearance equal rate of appearance. So I put that, I get to this equation. All right, now I have so many variables. I have the concentration of the enzyme, the concentration of the substrate. I have ES here, ES here. And if I want to solve for ES, I really need to replace some of the terms I have, like this enzyme concentration. I have total enzyme. The total enzyme is the free enzyme plus the enzyme plus substrate. Okay, so I want to get this total enzyme equal the enzyme free enzyme plus the complex enzyme. All right, then I can insert this, replace E with the enzyme, total enzyme minus ES. So if I want to replace this enzyme concentration, I can just replace it by E0 minus ES. All right, now I'm going to solve for ES. I'm going to do rearrangements. Just take ES out. Then I have K minus 1 plus K2 into ES, taking this one out. And then I'll do a little bit more algebra rearrangements. And then I get solve for ES, and I get this equation. All right, so I'm going to bring that. I'm just doing mathematical rearrangement to solve for ES. The same equation from the last page. Now, this here, I have a lot of rate constants. All of this is Km. So all of this is Km. Then now I have Km. I have the substrate, I have the total enzyme, and I have the enzyme to substrate ratio. Still, I need an equation where I have initial velocity in it. All right, so I go back to where my initial velocity is. Initial velocity is equal K2 into ES. All right. So I have the ES here, then I can replace, because now I want the initial velocity to be in the equation. Right? So I say, okay, then initial velocity equals K2 into all of this term. So now I have initial velocity, I have K2, I have Km, E0, S, and S. All right. I want to figure out a way to reduce my terms here. Don't want a lot of terms. So I'm bringing all of this into the next page. And then I would go say, okay, when all the enzyme is saturated, we have Vmax, because now I want to include Vmax in the equation. So Vmax is up here. I have saturation. All right, so this is what I know. Then I would go, okay, when I have concentration much higher than the Km, I have Vmax. And at this point, all of my enzyme is ES, it's saturated, right? So enzyme total equals the ES. Okay, so I can remove now E0 from here by stating, okay, so K2 into E0 will be replaced. Oh, I'm going back. Vmax equal K2 into E0. So I can take K2 into E0 and place it as Vmax. All right. Are you following? Do you want me to repeat anything? Where if you're lost somewhere, I can repeat. Okay, so I needed to get to an equation where I have Km, Vmax, substrate, and initial velocity. I needed to reach that from the beginning. So I had to make all these assumptions that allow me to get to this relationship. Okay, so it's very essential to say, when do I have the E0 or E total equal all of my complex? I have that when the enzyme is saturated up here. Then I can say all of my enzymes is in the form of ES. Then at this point, I have maximum velocity. So maximum velocity is when all of the enzyme is saturated. Then I can take K2 into E0 and say this is Vmax. And that's how I reach this equation. Any questions? Happy to repeat. I think it will take you a couple of times just to look through the derivation that I've done step by step. But I want you to remember that we wanted an equation that has Km, Vmax, initial velocity, and substrate. We control the initial substrate concentration because we are in control of it. And we can calculate initial velocity by monitoring product over time and getting the slope. And then we have this equation that we can utilize to solve for Vmax and Km. So that was all of the intention of this derivation. So you want to remember, each reaction and how we can calculate the rate of each of these reactions going forward, backward, and then utilizing what we know when the concentration of substrate is much larger than Km, then we are at Vmax, and so on. So when you think about it, just try to think about it step by step, and the ultimate goal is to reach this relation. You think about it when you're studying, and this might, the pieces will come together. I don't expect it now to be fully in your head, but definitely if you have questions, I can answer questions.
I have one question.
Yes,
So
sure.
this equation holds good only when the enzyme is saturated.
Yes.
It holds good in all situations.
No, it's not. Yes, it's this relationship to get to the Vmax, that's an assumption where the concentration is above Km. But you don't run your calculations only at the substrate concentration. You are running it at multiple substrate concentration, as I'll show you later. Well, as I showed you to get those initial V0, right? So that you will have a y-axis with V0 and an x-axis with substrate concentration. So you would run it above. But this is the relationship that you would get between V0, Vmax, and Km with all of these assumptions. Okay. So this is the Michaelis-Menten equation. So these are the two guys the brains that came up with this equation. But again, it's not a linear equation. So it's really hard to get your values out like that. If you make it into a linear equation, then you can do math better or easier. Then another couple of people, smart people, Lineweaver, Burke, to other people, came together and said, if we inverse Michaelis-Menten equation, we get a linear relationship. So the inverse is basically they took this equation and they inverted it. So now you plot, instead of plotting the initial velocities, you plot the inverse, 1 over the initial velocity. And instead of your x-axis being the substrate concentration, it will be 1 over the substrate concentration. Then everything is the inverse. So then you will have Km over Vmax, 1 over substrate concentration plus 1 over Vm. So what do we have? So that's basically your y equal ax plus b. So now your 1 over Vm is your intercept, that's v. And then 1 over the substrate concentration is your x. Instead of the x being substrate concentration, it's 1 over substrate concentration. And then the Km over Vmax is your slope, is your A. So now, when you plot your values, you will get y equal ax plus b. So you have a value for A, and then you have a value for B. So now you have the Vm, and you have the slope. You have the Vm, sorry, and the slope, we can calculate Vm. Right? So you have the slope. And then you have 1 over Vm is your intercept, so you can get the Vm by calculating 1 over the intercept. And then you have the Vm, you have the slope, you can get Km. Very cool. I mean, I did that as a postdoc. Of course, it was very cool. Okay, so yeah, that's great. So now we have a linear relationship. We can run our enzymatic reaction at different substrate concentration, get multiple initial velocities, plot the inverse of those, get the equation of the line, and solve for Km and Vmax. Let me show you what I did and how I used that. So one of my projects, I did multiple projects as a postdoc. One of my projects was looking at isoflavones in soy. So there were 3 main isoflavones in soy: diazine, ginseng, glycine. This is the general formula. They differ in the R1 and R2, but they have a glucose unit associated. They're not bioavailable like that. In order for us to absorb them, this glucose unit should be hydrolyzed. So we have glucosidases in our gut that breaks the glucosidic linkage here and allow us to absorb this glycone or the non-glycosylated unit. So I wanted to determine which of these are more bioavailable in our gut. So is the diazine, ginseng, or glycine more bioavailable? That means they will be more beneficial in terms of physiological properties. So I got a glycosidase glycosidase enzyme that is similar to what we have in the gut. and I did the kinetics of the reaction. And I plotted the lines. And I found that diazine and genesin are right here. If you look at the intercept, the one for glycitin has a higher intercept. That means the inverse of it, they will have lower velocity, lower initial velocity, because this is 1/v0. So a steeper slope means lower rate of the reaction. So if you have lower rate of the reaction, that means glycitin is the least bioavailable. So you can apply Lineweaver-Burke plot for different purposes, including determining the bioavailability of these phytochemicals. So that was cool. Yeah, so it has low Vmax and low catalytic efficiency, Kcat over Km. And Kcat is the Vmax over the total enzyme. The higher Km would have, and the lower Vmax, the lower is the catalytic efficiency. So that tells me that the enzyme was not efficient for glycitin in comparison to diazine and genesin. Is it time for a break? Yes, it's time for a break. I'll give you 5 minutes break. Yeah.
So you're saying, so I understand the higher the intercept here means lower V.
Vmax.
Oh, V max, not V.
And lower V0, but because this is the inverse relationship,
Sure.
right? So here the intercept
So, okay, so.
is this 1/Vmax. So the higher the intercept, that means the lower is the Vmax.
Okay.
Yeah.
Yeah, that makes sense.
Yeah, okay.
The lower V max translates to
Less,
lower K.
not less
Oh, higher.
not
No, no.
related, not related. Sometimes you have the same thing as but you have different. No. Yeah, they're not related. Yeah, no, so over the Vmax to the slope. Sometimes we have a constant Vmax that we have to sometimes we'll have a standard quantity but lower. So they're not, something that they don't go together. They're not one that is really maxes. Yeah, which when you put it's about half of the Vmax. The concentration people have half of the Vmax, so constant always. Supposed to become self-together when Vmax is high.
But it's so wide.
It's not. No, it's not, right? It's not like this increases this. They're not, there isn't no. Because the only category that the KM is the substrate when we have the Vmax, but the Vmax can be any. Right. So it's not dependent on the concentration first. You know what I mean? It's not, they don't move together. In energy. Yeah. So this one, we will look at the enzymes. No, it will increase the rate of the reaction, but it will not change how extracting the enzymes. The affinity is just the extraction. So basically, that is the thing. Yeah, it's not a thing. Yes. I need to go get water. I'll be back.
Yeah, why? That's bad, because this one is this. Oh, this one is this one. I thought this one. So the other is one, so it's just one. Right, so let's just stick this. That's one, so yeah, this one's lower because this one is bigger and longer and and see, I'm just looking at this. Yeah. Like, we just are yes, I hate this shot. It does not lower this is so that's the fire the slope is big down, the higher it goes down, and it's allowed like those lower the rest. This is back. Okay, and then the insect is larger, and this is number is smaller. Please numbers, yeah, this will be this the other one. But it's much smaller than where the reactions slow, yeah, slowly. So in some is basically so it might one over, yeah, so this one is larger, this one smaller. The smaller velocity means the reactions.
Yes.
Should be actually this one. The thing, the these and then I.
For the outside of this.
Think about it. We have the lower the divider. If we have lower divider. That. So you want to see the V so the wood, yeah, I would say I look at dividers, that's the to the lower dividers. Also.
You won't?
Yeah.
Yeah.
Oh, got it.
Thanks, baby.
Yeah.
Yeah. Yeah. Lower here, from the lower the lower.
Yeah, did you rest this weekend?
Friday, I didn't work, but Saturday and Sunday I was working full day. Yeah, I had to catch up,
How's Holly?
huh?
How's Holly?
Yeah, I caught up with Holly Sunday morning. We almost done with her manuscript. And then I worked with Leslie, and then on Saturday I worked for Rachel's first chapter, so. Yeah, and then did a lot of emails, gosh, the emails alone is. Yeah. All right, so we have everybody here. Okay. Let's continue. I think the toughest part with the brain is behind you a little bit. Okay, so when the enzyme is saturated, thank you, Ronnie. When the enzyme is saturated with substrate, then the reaction is dependent on the enzyme concentration. So as we increase the enzyme concentration, the velocity increases. Okay, that's the theoretical part, okay? But when we plot our, or when we plan our enzymatic reaction, so let's look at this graph and say, okay, 1 is enzyme concentration 1, 2 is enzyme concentration 2, 3rd enzyme concentration, 4th enzyme concentration. And as we go from 1 to 4, we're increasing the enzyme concentration. But look what happens to the actual line. The dotted is the actual data point. And then the solid line is your prediction line. So when you increase at any given time of the reaction, when you increase the enzyme concentration, the predicted is now deviated from the actual. Why? Can you tell me why? Why are we, the actual is like that? Versus straight.
Because like the reaction is too fast, so you use like, all the substrate.
Absolutely, thank you, Yi. Yes. So the reaction rate is so high, and then we are depleting the substrate. So now we are deviating from the prediction. So now our real reaction is going from linear into sloping into going to that plateau. So we don't want enzyme concentration number 4. We cannot control the reaction. We have to go, in order to be in the linear range where the prediction matches the actual, the reaction might be 30 seconds. We can do measurements in 30 seconds. We cannot just take absorbance at time. Look how emulsification stability is terrible for you guys, because it's so time dependent. So you don't want to work with a reaction that has linearity within 30 seconds. I want to choose an enzyme concentration and a time combination that I can actually measure my parameter without having to worry about it's only 30 seconds to pipette and to measure and all of that. So I would pick, let's say, 30 minutes with enzyme concentration 2, then the prediction is matching the actual. So I select my enzyme concentration based on the time of the reaction that I can control. So it's great to have a fast reaction, but we don't want it to be very fast. We want to make sure that the prediction matches the actual. Okay, so things to consider when you are making a reaction. Yeah, so this is just explaining that we want to maintain here, and we don't want it to be where it's sloping or curving. Yeah, that's what I say. Okay. Substrate concentration, we talked about that. So saturation, when the enzyme is, you're measuring enzyme activity, you don't want to, sometimes if you have really high in the substrate concentration, we get to inhibition, meaning that the substrate enzyme complex cannot go forward to produce a product. Because now the enzyme and substrate are binding, and there is a lot of substrate. Additional substrate might bind to the enzyme at different location, change the activity of the enzyme. So you don't want to be really at inhibiting concentration of the substrate. You want to be at the concentration where you activate the enzyme and you actually enhance the reaction. Okay. We're all familiar with this, right? So we've seen this before. If you've taken for the announcement, this is not new to you. As your temperature increase, you're enhancing the kinetic of the reaction. You're reaching an optimum that is great for the enzyme. And after reaching an optimum, we start seeing the decline because it's a protein. We start seeing the denaturation. So for, let's say, sometimes the denaturation temperature is about 60 or 70 degrees. Once you reach that, you start seeing a decline until you lose all activity because the protein is denatured. So it's not like with increase in temperature, you always see an increase in the rate. It's on the contrary because you have that denaturation. So you reach an optimum and then you see a decline. Okay, for pH, you have a bell shape. It's not always pH 6, by the way, or pH 7. Depends on the optimum for the enzyme. Sometimes the optimum pH is 8, sometimes the optimum pH is 2. But as you deviate from the optimum, you see an decrease in reaction both ways. If you go down in the pH or high in the pH away from the optimum, you'll see this change. But when you plot this, you don't want to always plot it based on pH 6 or 7 as the optimum. Sometimes I give you in the question, I tell you where the optimum pH is. So you want to make sure you put your optimum pH where you put the maximum velocity. Okay, so this is the enzyme activity. So this is the pH, you want to plot it based on the optimum. But then there is the stability pH, so this is different. The enzyme can be stable at low pH or high pH, but might not be active. Okay, so you can change the pH of the system, but the enzyme did not lose activity. Sometimes you can reduce the pH for whatever reason you are doing your reaction or your process, but the enzyme does not get inactivated. To inactivate, you might need to hit a extreme pH and maybe have some heat to inactivate. So there is pH stability and pH optimum, and you can measure pH stability by lowering or increasing the pH and then bringing it back to the optimum to see if you have the same activity. If you lose activity, that means whatever pH you dropped it to or increased it caused permanent denaturation. So at the optimum pH, you have the correct ionization necessary to get that stereospecific complexation of the enzyme and substrate. That's why there is an optimum pH, because enzymes are proteins, so they have different charges at different pH. And for every enzyme, you have to have a particular optimum pH to have maximum binding with the substrate. This explains what I talked about, that trypsin is stable. If you reduce the pH to 3, it's still stable. And when you bring back the pH to 7 or 8, then it will be active again. You don't lose or denature it like that. All right, so other environmental factors, we have cofactors. So there are needed for the enzyme to actually work. So there are 3 kinds of cofactors. You have the prophylactic groups. These bind very, very strongly when they are present with the enzyme. It's almost irreversible. So they bind, and it is a very strong interaction. And this is one example of a non-protein component, pyridoxal phosphate, for an aminotransferase enzyme. So this is an important cofactor for the enzyme to work, and it binds very, very strongly. Sometimes you need a certain organic ions. So sometimes you need either chloride or sodium or iron for an enzyme to actually function. And some of these enzymes are known as metalloproteases or metalloproteases. It's an example of a protease that require an organic ion for it. Of course, not all enzymes are proteases. This is just an example where organic ions need to be in the active site for the enzyme to function or to bind to the substrate. Coenzymes are just another non-enzyme or non-protein group like NAD. This is the reaction that we use in analysis to determine amount of ethanol that we have in the sample. So we add NAD and we use alcohol dehydrogenase. So this is a lyase because now we are creating a double bond. And so for the enzyme to function, we need this NAD cofactor. Inhibitors. So we have irreversible inhibitors. So like we have activation, we have inhibitors. So we have irreversible and reversible inhibitors. The irreversible inhibitors, they bind and the dissociation constant is very small. That means once they bind, you'll find very little free inhibitors in solution or dissociated in solution. So dissociation constant is very small. So the decrease in enzyme activity is related or directly related to the inhibitor concentration. Sometimes the complexation is slow. Let's say I want to determine amylase activity. If I want to use an amylase inhibitor to determine the amylase activity or residual amylase activity, I need to allow amylase inhibitor time to react with amylase before I measure the residual activity. This is the fun stuff. Reversible inhibitors. We utilize them or try to understand them a lot because they are present naturally sometimes, and sometimes we add them to inhibit certain reactions. All right, so we have three kinds of reversible inhibitors: competitive inhibition, non-competitive inhibition, and uncompetitive. So competitive, non-competitive, uncompetitive. So for competitive inhibition is very simple to understand. So basically you have a substrate and an enzyme. Look at the substrate succinate, for example, binds stereospecifically with the enzyme very nicely and give us a fumarate as a product and the enzyme back. A competitive inhibitor, meaning it competes with the substrate for the binding site. So this is another substrate. The inhibitor here in this case is melanin. Look at the structure of succinate and melanin. They differ only in one methyl group. So it can bind almost the same specifically with the enzyme. So it can bind, but no product is formed. So basically the substrate and the inhibitor are competing for the same binding site. So in this case, we have this kind of reaction. In competitive inhibition, once the substrate binds, we still have the same rate of the reaction. So when we plot the Lineweaver-Burke plot, we don't see a change in Vmax. So we still have the same intercept. What changes is Km. So with the inhibitor, the Km increases. So the enzyme loses affinity to the substrate because now the inhibitor is competing with the substrate. But once the substrate binds to the enzyme, same rate of the reaction happens. ES into product, so you have the same rate constant. It won't be affected. What is being impacted now is the affinity, because there's somebody else competing for that space. So when we have an inhibitor and we call it a good inhibitor, is that the Km of the inhibitor is lower. That means the enzyme have more affinity to the inhibitor than the substrate. So that is good because it slows down unwanted reactions. So we want to pick an inhibitor that actually have a lower Km than the substrate to that particular enzyme. So unless we have really high substrate concentration, that won't work. Then the more substrate concentration, the substrate will beat the inhibitor because you have higher substrate concentration. But if you have a lower Km for the inhibitor than the substrate, sometimes it's not desirable to have the inhibitor in that system if you want that reaction to happen. That means I want to produce a product. I'm using certain enzyme and substrate to produce a particular product. If I have an inhibitor with more affinity to my enzyme than the actual substrate, that's a problem. And that means I need to put much more substrate, and that will impact my rate of production. So it's kind of like the profit is less, and we need to move or inactivate that inhibitor to enhance my production. Okay, so there are times where it's good, times where it's not good. All right, so the next type of competition is non-competitive inhibition. In this case, the inhibitor and substrate are not competing for the binding site. So what happens is the inhibitor binds at a different location. When it binds at a different location, it's changed the molecular structure of the binding site. The substrate no longer binds. In this case, you're not changing the affinity, you're actually reducing the rate of the reaction. So in this case, we have Km is the same, but velocity is different. So this kind of a curve gives us an indication that the inhibitor is non-competitive inhibitor. This is not very common or commonly used, but just to have the complete picture, uncompetitive inhibition, this inhibitor binds to the ES complex. So once the ES complex is formed, the inhibitor binds. And if the inhibitor binds to the complex, then no product is being made. So this type of inhibition changes Km and Vmax. So it actually reduces the affinity, increases Km, and increases the and reduces the velocity. It does both. So we see kind of a parallel lines. But it's not very common application in food systems. This is an example of reversible inhibition. Also, I did that as a postdoc. That was another project. We worked on a plasmin enzyme in milk. Plasmin chews up casein and impact storage stability of milk over time. And in milk, we have plasmin inhibitors, we have plasminogen activators, so we have a complete complex system of these enzymes. So we were wanting to understand the natural plasmin inhibitors and how we can keep them active so that we can prevent the activity of plasmin, which would be detrimental to the quality. So we want to understand the plasmin inhibitor nature. So we ran the, of course, it took a lot of time to fractionate plasmin and inhibitor and activator. It was tragedy for me to get each of those components separated and then mixed together. Anyway, so when we put plasmin alone and plasmin plus the inhibitor, we saw that we have similar maximum velocity, different Km values. So what kind of competition is that? Competitive. So we calculated Km, we saw an increase in Km. So this is 9.38 times 10 to the negative 2, and then this is 5.1 times 10 to the negative 1. So Km increased. Vmax was not statistically different, 1.36 times 10 to the negative 3, 1.42 times 10 to the negative 6. Vmax was not different. Kcat and catalytic efficiency. So catalytic efficiency was reduced in the presence of the inhibitor because Km was higher. So we would deduce that, okay, that inhibitor is a competitive inhibitor in milk. That's another type of application where we're looking at polyphenol oxidase and different inhibitors. So there are two types of inhibitors here that you can see. One cause competitive inhibition, one cause non-competitive inhibition. In this case, we say that non-competitive inhibition is always better. Why? So we get the lower rate. That means I need less inhibition needed at any substrate level. So with less inhibition needed, with less inhibitor needing, that would reduce the cost. But sometimes the cost of the actual inhibitor might be high. We need to consider safety. How are we labeling it from a legal perspective? And if it has any sensory impact. So sometimes we have to look at what is beneficial overall, we have to also consider other things. So measurements. Who can define the unit of activity of an enzyme? That's a college board question. When I was a college board coach. What is the unit? How is it determined? Or what? One unit of enzyme activity, what does it mean? It's okay, you don't know. Sometimes I forget you. It's okay, but what it is the one unit of enzyme activity is the micromole per minute where substrate is converted, micromole of a substrate that is converted to a product in 1 minute at a specific pH, temperature, or energy. So we cannot always compare units of activities of two different enzymes. We have to look at the sheet for that enzyme to see what was the substrate they used, what was the pH, temperature, and ionic strength they used, so that we can relate apples to apples. So the same enzyme to a different substrate under different conditions will have different units of activity, right? So it is the micromole of a particular substrate per minute that is converted to product. And at a particular pH, temperature, and time. To pH, temperature, and ionic strength. So, however, concentration of enzyme is actually just grams, right? So grams, milligrams, amount of enzyme. So the amount of enzyme is different than unit of activity. So this is something that you want to remember, especially if you're doing enzymatic reactions. Okay, so if I'm measuring enzyme activity, what do I want my substrate to be? Much greater than Km or much lower than? Let's see how much you remember. Measuring enzyme activity, do I want it to be 0 order with respect to substrate or first order with respect to substrate? 0 order. So I want the substrate not to be the limiting factor. I want it to be saturating the enzyme. So I work with substrate concentration much greater than Km. Right? That's why I want to know my Km. Okay. So when I'm measuring enzymes, I want to measure it above the Km. When I'm measuring the constituents, the substrate, I want the opposite. I don't want the enzyme to be limiting. I want the concentration to be very low compared to Km, so I'm in that linear range. And then any change in the concentration of my constituents will impact the rate of reaction, and I can detect that and calculate the concentration of my. Oftentimes, I need to use a coupled reaction. Sometimes the measuring or auxiliary reaction doesn't give me any product that the substrate cannot absorb light. I cannot measure it easily, but that first reaction is essential. Then I need to couple it with another reaction. We call it indicating reaction. That will give me an absorption reading so that I can measure the activity or the substrate concentration effectively using spectrometry. So when I use coupled reactions and I have enzyme 1 and enzyme 2, I want to make sure that the enzymes work at similar optimum pH. Otherwise, it would be a disaster for me to change the pH during the reaction. So we try to find enzymes with similar optimum pH, and that second enzyme is not rate limiting. That means not slow, because that's my indicative reaction. So I don't want it to be the limiting reaction. This is an example where this is not the one that you use in the lab to measure fructose starch. There is a different coupled reaction for glucose. In this case, we use hexokinase, which is a transferase enzyme. So it's transferring a phosphate group from ATP to glucose. And then I use a dehydrogenase, which is a lyase enzyme. as my indicator reaction. By the way, auxiliary is the measuring reaction. And then this is the indicator reaction. So here the glucose 6-phosphate dehydrogenase, the lyase, that will convert NADP to NADPH, and I can measure absorption of NADH and use that to calculate glucose concentration. All right. So I'm not going to talk about all different types of all 6 classes of enzymes. I'm going to talk about the classes of enzymes that have a lot of relevance to foods. So hydrolases, we have a bunch of them. We're going to talk about pectinase, amylase, protease, lipase, lactase. Invertase is sucrase, by the way. So invertase converts sucrose into glucose and fructose. So we're going to talk about all of these hydrolases where water is taken up during the reaction. And oxidoreductase, we're going to talk about peroxidase, phenol oxidase, and glucose oxidase, different applications. So what's the definition of hydrolases? So we're breaking covalent bond, and what are we adding? Water, right? So the hydrolases is breaking triacylglycerol in this case, and then water molecules are taken up to produce fatty acid and diacylglycerol. But if I want to break all of the linkages, I need 3 H2O molecules to get 3 fatty acid and glycerol. So it's basically the uptake of water in the reaction. So pectinases. So we have different types of pectinases. One application, if we take the, pectins is made up of galactouronic acids, and sometimes the galactouronic acids are methylated. You have here a methyl group. Sometimes they have a methyl group, sometimes they don't have a methyl group. It's just an acid. So if you have a lot of low methoxy pectins, we form really good gels, because then if you put calcium in here, you would have this bonding with the negative charge. So sometimes you can take reduce the degree of the esterification by use of enzyme, and the enzyme is pectin methyl esterase. So the pectin methyl esterase is going to deesterify and release the COO minus. Then you can enhance the gel formation by with using a divalent ion. So this would be one type of pectinase enzyme. You also have the pectinases that actually break the bonds of the galactouronic acids. So here you have polymethyl galacturonase will break a bond after you have a methyl group, and the polygalacturonase will break the bond when you don't have a methyl group. So you have 2 types of enzymes, and they can be endo or exo enzymes to break down the bonds of pectin. So this is a common enzyme or combination of enzymes that is used to clarify apple juice. So in apple juice, if you use polymethyl galacturonase and polygalacturonase, both of them, you use them, it will break down the pulp and you get clear apple juice. It's a common utilization. Pectin methyl esterase. So, in orange juice, you don't want that. Sometimes you want your pulp in your orange juice, and you don't want it to separate. You don't want the separation. You want to keep the pulp in your orange juice without separation. So there is an native to the orange juice. You have pectin methyl esterase. And if it's negative, it's going to break the method, deacidify, and then enhance the potential of forming aggregation of these pulp and separation due to reaction with ions in the system or divalent ions in the system. So in order to prevent the separation in pulp, we want to inactivate pectin methyl esterases. So you want to inactivate, you want to treat the orange juice to inactivate this enzyme so that you don't have this pulp separation. So this is a case study where they looked at using temperature combined with pressure to look at inactivation kinetics of that enzyme. So you don't want to heat too high, you don't want to change the flavor of your orange juice or too high the temperature too long of a time. You change the organoleptic properties of the juice. So this was looking at what can we do to combine pressure and temperature to reduce the activity or inactivate methyl ester. So they did a combination of different pressures and different temperature. They looked at the rate constant of inactivation, and they looked at the D value, which I think is the time to cause 10-fold reduction in activity, right? You guys should know this from microbiology, the D value. 10-fold reduction in activity? Okay. So what happens here, they found that combining 400 with, or 600 with 50 degrees of temperature, you got the highest rate constant of inactivation and the lowest time. So in only 4 minutes, you get 10-fold reduction in activity. Okay, and the next case study, well, I thought I had another case study, but I don't. All right, the next one is amylases. So amylases are important. One main use of amylases is first for production of high fructose corn syrup, or production of the different corn syrups that have different dextrose equivalent. So, and we utilize amylases to also amylize total starch, total damaged starch, or amylase to amylopectin ratio. So we use it in analysis. We use amylases in analysis a lot. So you have the carbohydrate, and then each of these enzymes have different specificity. So you've seen this before, maybe in chem and food analysis. So here we have the alpha amylases, which is an endo enzyme. It can cut alpha-1,4 linkages. It can also cut alpha-1,6 linkages as well. Oh, no, it cuts alpha-1,4 here and alpha-1,4 in the chain. But what cuts alpha-1,6 linkages can be glucoamylase, and also it cuts single glucose units. And then you have the beta amylase that cuts 2 units at a time, 2 or 3 units at a time. It's an exon enzyme. And then you have the prolinase, which is very specific to alpha-1,6 linkages. So depending on if you have gelatinized starch, non-gelatinized starch, or what do you want to get at the end, use a combination of these enzymes. So prolinase and beta amylase, the starch has to be gelatinized for them to work specifically. Otherwise, they won't have any activity on the starch. But this is a main application. You have starch, use alpha amylase, you get dextrin, maltodextrin. Use glucoamylase, you get glucose units. Use glucose isomerase, which is not a hydrolase, by the way. Don't confuse that. It's an isomerase. So you can change glucose to fructose, and then you can have the high fructose corn syrup. Lactase is used a lot to, if you get rid of lactose in milk or milk, ice cream, yogurt. For lactose intolerance people, sometimes lactose intolerance people can also put the enzyme on whatever food they're eating that might have lactose in it. So it just converts, breaks down lactose into glucose and galactose. That's the main application for it. Sucrase or invertase, main application is the cherry covered, chocolate covered cherry. So if we use sucrose, and what happens is over time sucrose crystallizes, then you don't have that syrupy texture, soft syrupy texture. So when you produce this, they add sucrase or invertase, and then you would have this glucose and fructose that will maintain a syrupy texture. So it doesn't crystallize over time. Proteases, lots of application. We added to formation of cheese. We'll talk more about that in the dairy protein class lecture. It's used for meat tenderization and beef cuts. For example, you add bromelain, for example, to tenderize the meat. Disrupt gels when you don't use gels to form. During aging, so give you a flavor by breaking down proteins into peptides. Bioactivity enhances the production of peptides with physiological activity. And sometimes we add them if you have really strong wheat and you want some extensibility in the dough, and break down the gluten forming proteins to reduce the elasticity. So lots of application for proteases, enhanced functionality in protein ingredients as well. So this is a table that just shows you examples of different proteinases or proteases. Also what you have in the active side, sometimes they're called serine endoproteases. That means we have a serine hydroxyl group in the active side. Sometimes they're called metallo and proteinases. They need metallic ion for them to be active. So different specificity, different activity of these enzymes. Lipases, they are used to impact flavor. So naturally in ripening, you break down some lipids, you form unique flavors. Sometimes you use them to produce monoacylglycerol, diacylglycerol to enhance emulsification and produce tailor-made lipids. So these are the application. What's the definition of oxidoreductase? Says. Okay, you're all tired. Enzymes that oxidize or reduce substrate. So we have a transfer of hydrogen or electrons and involving oxygen. So we have catalase, which is the common name for peroxidase. Peroxidase is an oxidizing oxidoreductase enzyme that catalyzes the conversion of peroxide into water and oxygen. So polyphenol oxidase is a very common oxidoreductase. So it's an enzymatic browning, of course. So it causes browning. Sometimes it's desirable, like in tea. And sometimes it's not desirable, like in shrimp. So they call it shrimp melanosis when the shrimp turns brown like that. I mean, it's not desirable, but it does not necessarily impact maybe the taste or the texture. It just doesn't look good. And then, of course, browning in fruits. What's so unique about Granny Smith? You cut Granny Smith and you don't see browning very fast. Huh? Breeding. Yeah. So we genetic engineering to reduce the polyphenol oxidase content. So this is the reaction. So you have, in the presence of, polyphenol oxidase, the first one is actually you generate polyphenol, so you get diphenol. And then you take that, gets oxidized into quinone. And then there is a condensation reaction called polymerization. This is non-enzymatic. It just, condensation, polymerization, you get the monoamines. So we can intervene by adding a reducing agent, goes quinone, reduces it back to diphenol. So we can add ascorbic acid, thiol compounds, or sodium bisulfite as reducing agents. Or we can add sulfite to form sulfur adduct. So once the sulfur adduct is formed, we don't get that polymerization. So you can intervene here in the middle. So there are different ways to inhibit or inactivate. So heat treatment, removal of moisture, acidification, because then the pH is not ideal for the reaction, reducing agent, chelating agent, so hanging on to metals that would enhance the reaction. So chelate the metals, adding competitive inhibitors, modified atmosphere packaging, remove the air and put nitrogen, for example, or argon gas. And then genetic engineering, knock it off. Irradiation, high pressure processing, so many different ways to get rid of polyphenol oxidase. So this is case one, where we looked at enzyme kinetics to understand differences of polyphenol enzymes from two different species of peaches. What were they specific to what substrates, and what inhibitor can be used? So here, they found that for one enzyme, it has better affinity to one particular substrate, another enzyme has a better affinity to another substrate. So it is polyphenol oxidase from peaches, but two different varieties. So they wanted to understand the Km, the affinity, they want to understand Emax, get the catalytic efficiency so that they can combat this enzyme. They looked at inhibitors. So most of the inhibitors turned out to be competitive inhibition, and figured out which ones really reduce the reaction kinetic or rate constant of the reaction for the different. It turned out that one inhibitor was good for both enzymes. So this is just an application of kinetics. Here they looked at using modified atmospheric packaging, and what they did is they changed the atmosphere from air to argon, air and nitrogen for two different types of polyphenol oxidase, from mushroom and from apple. You can see that in all cases, Vmax was the same, but Km was different. So the highest Km in this case was 97% argon, and also the highest Km was the 97% argon. So basically we reduce the affinity of the substrate to the enzyme in the presence of argon. So what kind of inhibition is that? Competitive, yeah. Okay. I'm getting here to the end, 5 minutes and I'll be done. So glucose oxidase, we use that input analysis to determine total glucose. Mostly you hydrolyze your starch to determine total starch, or amylose amylopectin, or damaged starch. And once you get to glucose, the one that you do in the lab is different from the other equation or chemical reaction. We use glucose oxidase, and then we use peroxidase or catalase. That's reaction 1, reaction 2. you get an oxidized dye. So here you don't have a color, and then you generate an oxidized dye with a color, and you measure the absorption, convert to glucose concentration with a standard. We utilize glucose oxidase as an oxygen scavenger in bioactive packaging. So we immobilize the enzyme in the interior of the packaging, and it will utilize the oxygen to prevent the oxidation, like lipid oxidation, for example. So it acts as a scavenger. So basically that's immobilized and helps with reducing the oxygen in the package. So where do we apply immobilized enzymes? The industry application is for production of high fructose corn syrup, hydrolysis of lactose in milk, production of protein hydrolysate, and in ELISA, enzyme-linked immunosorbent assays. So we immobilize the enzymes on an antibody or on an antigen for that reaction. So here are a few examples of using enzymes in baking. Alpha amylase is used, added sometimes to enhance fermentation during the formation of the dough or fermentation of the dough, or also it can cleave the starch to prevent staining, so enhance the shelf life of bread. Sometimes we add proteases to break down gluten-forming proteins to make better rheological properties. The glutamyl transferase is the same as transglutaminase. It's the same, the different utilization of where to place the wording, but it's the same. Sometimes it enhances polymerization, so enhance elasticity. Sulfhydryl oxidase enhances formation of disulfide linkages. So these are examples. In bread making as well, we can use transglutaminase for no gluten or breads like rice bread. We talked about that earlier in the semester. In dairy, chymosin proteins, proteases during cheese ripening, lipases also during cheese ripening, removal of sulfide groups to remove cooked flavor, remove galactosidases is the same as lactase, just a different name for the same enzyme, also removal of lactase. So microbial protease, I don't know why they put them. This is an old table from I don't know which book. They put soy. It's not dairy, obviously, but helps with coagulation, apparently, of soy. All right, so here, unwanted removal of unwanted constituents. We gave the lactase, galactosidase is the same, catalase to remove hydrogen peroxide, other enzymes, proteases to debitter, and sometimes you add proteases to get rid of protease inhibitors, because protease inhibitors are proteins as well. All right, so this is just throwback to food analysis lecture. When you want to measure different constituents, remember substrate concentration much smaller than Km. So sulfide for labeling, we want to make sure that sulfide is below certain concentration, so that if it's above, we need to put it on the label for people with sulfide sensitivity, measuring glucose, measuring starch, talk about that. D-malic acid is the synthetic form of malic acid in apple, and natural malic acid in apple is aliform. So if the apple juice is not natural, we can detect that by measuring D-malic acid. These are enzymes that we measure. Siloxidase determines the success of blanching. Lipoxygenase, sometimes we measure it to determine oxidative acidity potential, or also it's an indicator of blanching. So these are thermally stable enzymes. If they were inactivated, that means branching was successful. Alpha amylase, that is a common test we do in flour. High concentration of alpha amylase impact the starch functionality, reduces the viscosity in different applications. Rennet, we determine the activity of rennet so that we know how much to add for cheese making and so on. Okay, so these are just examples. And I'm done with enzymes. Woohoo! Okay, so we start daily on Wednesday and we have a presenting group. All right. Cool. Thank you. Go rest. Have a good dinner. Yes.
Enzymes.
Yes.